All right. In today's lesson, section 2.2 in our Big Ideas textbook, we've got a couple of things we're going to cover. Today we're just going to focus on exploring the properties of parabolas. Tomorrow we'll talk about max and min. We will be graphing quadratics today, but we will not be using x-intercepts for that. So today we're just going to focus on some of the basics of what parabolas have all in common. So with that said, let's first take and look at a parabola. Now this parabola's equation is y equals x minus 2 squared plus 1. And we learned yesterday that, and the day before, that this is in vertex form. And our vertex is always going to be located at h, k. And so our vertex is right there. We can see if we compare this vertex form to the actual function we have, y equals x minus 2 squared plus 1, we can see the h value is 2 and the k value is 1. Oops. And so our vertex is located right where I have the arrow. Okay, and that is the ordered pair 2, 1. It is 1, 2 in the x and 1 in the y. This also follows the, because the a value is just 1, there's a 1 in front of here, we just don't show it. It looks just like the parent function y equals x squared. If you remember, parent function starts at the origin usually, in this case, so it's been shifted, but it does 1, 1, that points on it. It does 2, 4, 1, 2, 3, 4. It also does negative 1, 1, and negative 2, 4. So we can generate those points just by using the parent function, y equals x squared, but counting from this vertex where it's been shifted to. You'll also notice in this drawing that we have this dotted line right here. Okay, this dotted line is called the axis of symmetry. All parabolas have an axis of symmetry. It's called the axis of symmetry because this is where the parabola can be folded over on itself and its points would match up with each other from left to right. And that one point where it lies on the axis, that is our vertex, or where the parabola crosses the axis of symmetry. Now this axis of symmetry actually has an equation. It is a vertical line. All vertical lines have the same equation. It is always x equals and whatever x value it goes through. So in this case, it always goes through x is always 2, which is also the h value. So on all of our parabolas, whatever your h value is, x equals h is the formula for the axis of symmetry. Now we're going to use all these concepts here to help us graph parabolas, okay, and make them look as accurate as we can. Now I know, again, you guys are going to be working probably on paper that doesn't have a coordinate axis grid on it, but that's all right. We can still do it, and I'll model that for you so you can see how you can do it by hand on a piece of paper. So let's look at our first example here. Okay, we want to graph this function here. Now remember, this f of x notation, you can also rewrite that as just y equals negative 2 times x plus 3 quantity squared plus 4. This is in vertex form, a times x minus h quantity squared plus k. Now, a couple of things. Before you even start graphing it, you want to try and get an idea of what's going on here. The a value is negative, which means it's going to open upside down. Okay, look like the St. Louis Arch, essentially. The 2, which is bigger than 1, means it's going to be narrower than the parent function. Because we have an x plus 3, it's going to be shifted. We have to decide if it's shifted left or right. Remember, always ask yourself, what would make this 0 in here? In this case, x, if it was -3, -3 plus 3 is 0. That -3 tells us it's going to be shifted to the left, and this 4 is going to shift it up or down. In this case, it's a +4, so it's going to be shifted up 4. So let's first find or write down our vertex, because that's always an important question. The vertex for this thing, this parabola, is going to be at, h has to be a -3. We just talked about y, and the k is a +4. So let's go ahead and draw a coordinate axis. Just do the best you can on your paper. You've got at least lines on your paper, so it can help you get horizontal and hopefully get you vertical. Let's mark that vertex. -3 in the x and +4 in the y. So our vertex is going to be right there, and I'm going to label him with a V. And let's go ahead, -3, 4. Next, let's write our axis of symmetry. Remember, the axis of symmetry is x equals h. So in this case, x equals -3, our h value. Let me mark that right here, hk. All right, and so that -3 for x, there's where the x's are always -3. It's this vertical line right there. So let's go ahead and draw that in. Lastly, now we have to generate some points. Now, the way to generate these points, the easy way, is to use that a value and just put x squared behind it. And watch what happens as I generate these points. When x is 0, 0 squared is 0, 0 times anything is 0. When x is 1, 1 squared is 1, times -2 is -2. And when x squared is, or when x is 2, 2 squared is 4, times -2 is -8. Now what's key, because I just used -2x squared, I haven't used any of this 3 or this 4 when I did my calculations. What that means is I can just count from this vertex that I found. This is like my 0, 0. Then it says when x is 1, y is down 2. So I just go down 2. So I moved over 1 from my vertex because x is 1 and down 2. And that's going to be another point on my parabola. So right about there. And symmetry now tells me that across from this, let me put a mark right here, I will have a mirror image of that point right there. So that's where symmetry about that axis of symmetry comes in. My next point says count from the origin, but my origin now is this new vertex. It says go over 2 in the x, 1, 2, and it says go down 8. 1, 2, 3, 4, 5, 6, 7, 8. So we'll put some marks in. 1, 2, 3, 4, 5, 6, 7, 8. So I've gone over 2 from my vertex and down 1, 2, 3, 4, 5, 6, 7, 8, and I'm going to have another point right there. So let's put a point down there. And then symmetry tells me I'll have one on the other side of that axis of symmetry, just perfectly even with it right about there. And you can see this parabola, as I draw it in, is narrower than the parent function. Opens upside down like we predicted. And it has the correct vertex. Now, if you did not do it this way, then it becomes problematic because you're going to have to do a lot more math. If I actually wanted to use the entire equation, I wanted to make a little table, I can find my vertex the same way, -3, 4. That's no problem. But now, if I were to plug in 0, for example, in fact, I don't want to plug in 0, I'm going to plug in -2, and you'll see why in a second. So if I was to use the full equation, I'd have to take this -2 and go -2 plus 3 is 1. 1 squared is 1. 1 times -2 is -2. That -2 plus 4 is 2. So I can do the math to find the ordered pair from this big equation, but if I use the big equation, I have to count from the origin. -2, +2. It just gives me this point right here. So it's much easier to generate points with this smaller equation and just count from your vertex to get your graph. Makes it quick, makes it simple, makes it easy. We already knew it was going to be upside down, it was going to be narrow, it'd start at -3, 4, and then we can just generate some points to count from our vertex.
All right, now we're going to talk about standard form. So we've been talking of quadratic functions. We've been talking about vertex form. Remember vertex form again. A times x minus h squared plus k. And vertex form is awesome because you can find the vertex very, very quickly. You know the direction it's going to open. You know if it's narrow or if it's going to be wide, whether it's stretched in the y direction or it's shrunk in the y direction. Standard form is another way to write quadratic functions. This is probably the more common way that you'll see quadratic functions written. Okay. You'll notice ax squared plus bx plus c. This a is the same a that we saw in vertex form. So we've used the same variable for it. So that a value is still going to tell you if it opens up or opens down. Positive opens up, negative opens down. If it's bigger than 1, it's going to be narrow, and if it's a fraction between 0 and 1, it will be wide. So that's the same a. But we cannot tell the vertex straight away just by looking at it when it's in standard form. Okay, if you look down here at this core concept from our book, so here is the quadratic function in standard form. And again, it says a is greater than 0. Notice it shows it opening upward. Here is the same form, standard form, but if a is less than 0, if it's negative, it opens down. Some other things you want to note on this slide. The first one is the axis of symmetry. Okay, that helps us figure out points. Is calculated with -b over 2a. So we're talking about the b here next to the x to the first power term, the linear term, over 2 times a, that a term. Same thing if it opens downward, -b over 2a. So that's going to be an important expression for us. The other thing is the c value is your y-intercept where it crosses the y-axis. So just like we had lines and we looked at their y-intercepts, parabolas have y-intercepts as well. And we just have to find that c value, whatever c is where it crosses the y-axis. So it's cool because if we know the axis of symmetry and we know the y-intercept, we also know a mirrored point or a symmetric point across from it. Okay, so just reading along here, the parabola opens up when a is greater than 0, down when a is less than 0. The graph is narrower than the parent function when the absolute value of a is greater than 1. Okay, so if we're 2, 3, 4, 5, 6, those numbers are bigger than 1. They say absolute value because we want to ignore the negative sign. The negative just tells us up or down, but it's the absolute value of a that tells us if it's going to be narrow or if it's going to be wide, and it will be wider when the absolute value is less than 1, so that decimal value between -1 and 1. Axis of symmetry, -b over 2a. The vertex is a little bit complicated. The x value is the x value of the axis of symmetry, but the y value has to be calculated, and we'll explain that on the next slide. And the y-intercept is c, so 0c is on the parabola. That's that point we just talked about. So let's take a look at a parabola that is in standard form. We got to do a few things to it. They want us to label the vertex and the axis of symmetry. And we're going to graph this guy, but we can do a lot of work before we even start graphing him. First of all, let's identify what a is. A is equal to 3. That 3 being bigger than 1 tells us the parabola is going to be a narrow one. It's also positive, which means it's going to open up. We know that right away. We cannot tell the vertex yet, but we can find the axis of symmetry. The axis of symmetry is always at negative b over 2a. So let's locate our a, b, and c. I'm going to blow this up just a tad. This is a and x squared plus bx plus c. Notice b must be a negative 6. So it's negative, and b is negative 6. So we get the double negative because the formula has a negative in it, over 2 times a, and you can see our a value is just a 3 right there. So double negatives make it a positive 6 over 6. So the x value is 1, and that is our axis of symmetry. So if I was going to start graphing this right now, what I do know is my axis of symmetry is right here, where x is equal to 1. And I know my parabola is going to open upward, and it's going to be narrow. Now let's talk about this vertex formula over here. It says the vertex is at negative b over 2a, comma, f of negative b over 2a. Okay, well, our function, I already know what negative b over 2a is, my vertex. I just found out the axis of symmetry is at 1, and negative 1 was calculated with negative b over 2a. So I know the x value of the vertex. I know my vertex has to be on this axis of symmetry. So the f of negative b over 2a just means take your function up here, f, and plug in what the value is of negative b over 2a, which is 1. So I really want the f of 1. Okay, so here's my function. I'm going to write it down here a little bit bigger. F of x equals 3x squared minus 6x plus 1. I want the f of negative b over 2a, which is equal to 1, so I want the f of 1. So 3, and then I substitute in a 1 wherever I see an x. Note I'm using parentheses to keep things organized. Order of operations, I have to square the 1 first, which is 1, and 1 times 3 is 3. I have to do multiplication next, so negative 6 times 1, negative 6. I add and subtract left to right, so 3 minus 6 is negative 3. I get negative 2. And I've shown every single step in there, so you can see it all. But that means my vertex is at 1, negative 2. So let's go back to our graph over here. Let's go ahead and mark 1, negative 2. Put in a few more hash marks. 1, negative 2 is right there, and that is my vertex. I can also find my y-intercept. My y-intercept, if you recall, is the c value. In this case, c is 1. And that's my y-intercept. So let's go ahead and mark that guy right here. And now because of symmetry, I know there's another point right across from him. All right? And in general, when you're doing this by hand, that's enough points. Maybe we'd like another one, but that's not too bad. And there is the graph of my parabola. Okay. Now, I can actually generate more points from this. We talked about this in yesterday's assignment, or earlier in this assignment. I could just use that a value, y equals 3x squared. I'm going to generate a few points with him. 0 squared is 0 times 3 is 0. X is 1. 1 squared is 1 times 3 is 3. 2 squared is 4. 4 times 3 is 12. But if I use this little mini function where I've gotten rid of this bx and gotten rid of that c term, I just have to count from the vertex. This is my 0, 0. Here is 1, and then 1, 2, 3, that point that I already had. if I wanted another point, I could count over 2, 1, 2, and then I could go up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and over at 2, 2 right there, over 2, up 12 would put me right there, and it would give me another pair of points. Now, we don't have to have that many points. I just wanted to illustrate that by using this little function, I can actually find points if I count from these transformed or translated vertex. And that's all there is to graphing these things. Now we're going to look at a couple more examples here. All right, so let's go ahead and look at how we can apply some of the things we've just been talking about to these two problems. These are examples out of your book. And we just have to graph these. But we're going to go ahead and use some of the concepts to try and describe everything we can and know about them right now. So this first one, number 1 here, this is written in vertex form. Y equals a times x minus h squared plus k. But we have f of x in place of y, but that's fine. They mean the same thing. Our a is negative 3, x plus 1, and they have nothing out there on the right-hand side, so that essentially just means it's a plus 0. There's nothing added on. Okay, so we can find our vertex really quick, vertex of this parabola, because we are in vertex form. Remember, we ask ourselves what makes this 0 inside. Negative 1 would. So our h value is negative 1. It's x minus negative 1, which is an x plus 1. So h is negative 1, and k is the number that's out here, but that we already said was 0. So there's our vertex. Our axis of symmetry, that line that our parabola could fold over on, is always x equals h. So in our case, x equals negative 1. Remember, this is the ordered pair h, k when we're talking about vertex. And so let's start to graph him. I mean, we know a lot about him, and we haven't really done any math. We know where his vertex is. I'm going to make a few tick marks here. Probably going to need more, but that's all right. Vertex, negative 1, 0. There he is. Axis of symmetry. That is a vertical line at x is negative 1. It always goes through the vertex. So there's our axis of symmetry. We show that with a dashed line. Okay. We know it opens downward. A is negative 3. That means it opens down, so we know it's upside down, like the St. Louis Arch. Y-intercept, we don't know that because it's not in vertex or not in standard form. So let's just generate a few values. Now to generate those values, you just use y equals negative 3x squared. Forget about the h and k values. 0 gives me 0. That'll always be true. 0 squared is 0 times anything is 0. 1 squared is 1 times negative 3 is negative 3. 2 squared is 4. 4 times negative 3 is negative 12. And so again, watch how I count. You count from that vertex. The x is 1, negative 3. 1, 2, 3. Right there is another point that it goes through. So we're going to put a point right there. Symmetry tells me there's another matching point right across from it, one way or 1 unit away from that axis of symmetry. I could also count over 2 and go down 12. 3, 4, I don't want to count that far, so I'm going to sketch it in, trying to make it as smooth as I can. So it's a narrow function, it's upside down, it's parabolic, and its vertex is at negative 1, 0. And we are done. Let's shrink all that work up, hopefully. Oh, it won't let me just do that part of it. That's all right. We got plenty of room to do 3 here on the left-hand side. This one, number 3 here, is in standard form. ax squared plus bx plus c. All right, a little bit tougher to work with. We do know the a value, which is the number in front of the x squared, is a 1. That means it's going to have the same shape as y equals x squared, the parent function. Okay, we also know a is positive, so it's going to open upward. We just got to figure out its vertex and y-axis of symmetry and y-intercept, and we'll be good to go. All right, so let's find first the axis of symmetry. Negative b over 2a. Let's highlight these values for you so you can see them. A is 1, b is 2, c is negative 1. So we'll have negative of b. b is 2 over 2 times a, which is 1, which is negative 2 over 2, which is negative 1. Axis of symmetry. And you can even start graphing at this point. Here's negative 1. Axis of symmetry is at negative 1. Right there. I just don't know how high up or how low down the y value is of the vertex. That's all right. All you have to do, I call it back solving. You take this negative 1. You know the x value of the vertex. I'm guaranteed this vertex is at negative 1. There's the x. I just don't know the y. Well, how do you find the y? Substitute that x value in. And so to find our y value of our vertex, it is, in place of the x, I'm putting negative 1 squared plus 2 times negative 1 minus 1. Negative 1 times negative 1 is 1. 2 times negative 1 is negative 2 minus 1. 1 minus 2, negative 1 minus 1 equals negative 2. There's where my vertex is. Find the x value of the vertex by locating the axis of symmetry, substitute it into the equation, and find the y value. Let's mark that negative 2. And so my vertex is negative 1, negative 2. My y-intercept is the c value, negative 1 up here. So my y-intercept is right there. And symmetry tells me then 1 away on the other side will be another point on my parabola. Now, because my a value is 1, this looks just like y equals x squared. Remember those values. We've talked about them like 3 times now. 0, 0, 1, 1, 2, 4. And if we count from the vertex, this is 0, 0. This is 1, 1. But I can also do 1, 2, and then up 4. So I'm going to mark a few more tick marks. Let's do them in black. And I'm going to just count over 2, 1, 2, up 4, 1, 2, 3, 4. Right there is a point on my parabola. And then there's a matching point on the other side, his symmetric point. And my parabola looks something like that. And we're done. And that's it. So now we can graph, hopefully, from vertex form or standard form, and do it by hand on a piece of paper and have a pretty darn accurate graph.